Welcome! It's time to assess the performance of our PD model. To do that, we can use the data we put aside when we split the dataset into train and test. Just a quick reminder, we used the train dataset to train the model, and now we're going to use the test dataset to test it. As you probably recall, we stored the test data in the Lone Data Inputs Test data frame. Once again, we must select only the relevant columns from the test data frame, as we did with the train data. So let inputs test with reference categories equal lone data inputs test all rows and the same list of columns we selected for inputs train with reference categories. You can notice that in the reference categories list from above, we already have the names of the dummy variables that serve as reference categories. Just in case, let's have them here as well. Now we can proceed in the exact same way as we did before to preserve only the variables we need for the model. In the case of the train data, we needed these variables to estimate the model. Now with the test data, we need the exact same variables to apply the model. So let inputs test be equal to the inputs test with reference categories data frame with the variables itemized in the reference categories list dropped. As a result, here, in the inputs test data frame, for each observation from the test dataset, we have the same 84 variables that were used for training. Great! Now we will use our model to estimate the probability of default of each observation from the test data. Let's do that. Let y hat test be equal to reg2.model.predict from inputs test data frame. This statement takes the model, which is stored in the reg2 object, and applies the predict method on it with the test inputs as its only argument. Here's how it works behind the scenes. First, the predict method multiplies the values of the variables of each observation by the estimated model coefficients. This yields the log of odds and non-default, or being a good borrower. Then, an exponent is raised to the power this log odds, and thus the odds themselves are obtained. From there, the estimated probability of non-default, or being a good borrower, is obtained directly. Finally, the results are categorized into non-default or good and default or bad by applying a cutoff to this probability. The default cutoff is 0.5 or 50%. When this cutoff is applied, all observations with estimated probabilities of being good less than 0.5 would be classified as bad, or 0. Alternatively, all observations with estimated probabilities of being good greater than 50% would be classified as good, or 1. Thus, y hat test is an array of zeros and ones, one for each of the observations in the input test data frame. Of course, there are other possible cutoffs as well. For example, we may consider that all estimated probabilities below 0.3 will count as predicted bad borrowers, and all estimated probabilities above 0.3 as predicted good borrowers. In the same way, we may select any value between 0 and 1 to be the cutoff. So in order to assess how well our PD model performs, it is much more important to obtain the raw predicted probabilities for each observation in the test dataset, rather than the categories predicted by the predict method. To achieve that, we can use another method, predict proba. To start off, we can create another variable called y hat test proba. Let it be equal to reg2.model.predict_proba from inputs test data frame. Now the y hat test proba is an array of arrays, as many as there are observations in the inputs test data frame. Each of these arrays is composed of two elements. The first element is the probability of default, or the probability of being a bad borrower. And the second element is the probability of non-default, or the probability of being a good borrower. Of course, as you already know, there is a one-to-one correspondence between these two probabilities. The probability of non-default equals 1 minus the probability of default. So as expected, the only piece of information we need in order to represent the statistics that describe model performance in the widely accepted format is the probability of non-default, that is, the probability of being a good borrower. Okay, let's create a new array where each element is equal to the second element of each of these arrays. We can overwrite y hat test proba itself with that. In terms of code, to select only the second column, we choose all arrays and then, from each array, only the second element. Note that the second element has an index of 1. Great! Now, y hat test proba is an array containing only the probabilities of being a good borrower. For convenience, we can put the actual good-bad variable and the estimated probabilities in one data frame. Let df actual predicted probs equal pd concat from a list containing data frames of the two arrays, the lone data targets test and y hat test proba with the estimated probabilities of being a good borrower. This new e-data frame contains 2 columns and 93,257 observations. Let's name the columns lone data targets test and y hat test proba. I prefer indexing the newly created data frame exactly as the lone data inputs test and lone data targets test data frames. We can easily do that if we set the index of the new data frame to equal the index of either one, as their indexes are the same. Say the indexes of lone data inputs test. Great! We have our data frame with actual good-bad values and probabilities of being good or bad. It's estimated by our PD model and is all set. So now, I think it's time to calculate and visualize some metrics that will show us how well our PD model performs. See you in the next lecture. Thanks for watching.